We were talking about hydrogen bonding the last time, which is one kind of these 6 intermolecular forces, which are found in... This computer is acting a little fidgety, and it's making me nervous. Table 12 point, I couldn't remember if it was table or figure. It's got art, sometimes things with artwork are figure. This is table 12.2. And we didn't talk about a lot about the hydrogen bonding, thus we got to get into it now. So hydrogen bonding is a very, very, very important kind of intermolecular force to understand and appreciate. Again, we're talking intermolecular forces here. We're talking about forces between molecules. That is going, that's good. Forces between molecules. In a hydrogen bonding situation, what you need to look for is 2 atoms, two atoms on different molecules of either N, O, or F, nitrogen, oxygen, or fluorine, at least one of which is bonded to hydrogen with a covalent bond. So in this cartoon representation here, A and B are both NO or F. They don't have to be the same. That is to say, A could be nitrogen and B could be oxygen, or vice versa, or they could both be nitrogen, whatever. Okay. So A and B are both either N, O, or F, and the hydrogen bond is where that ... is in between. The reason it's NO or F that's involved is that a bond between NO or F and hydrogen is very polar, right? Recall electronegativity and polarity of a bond because of the difference in electronegativity. Nitrogen, oxygen, fluorine, when they bond to hydrogen with a covalent bond, the bond is very polar. Chlorine, if you look at the values of electronegativity, chlorine has the same electronegativity to 2 sig figs as nitrogen does. Chlorine's not involved in this. Chlorine's too big. Okay, it has to be both electronegative and small. Okay, so nice small atom, it's very electronegative. An HCl bond is not polar enough to exhibit this as much as the other ones, even though it's the same electronegativity. It has to do with the size as well. So here are 2 water molecules. They have hydrogen bonds between them. But there are other molecules, like if you had ammonia, they would form hydrogen bonds, and we'll deal with a couple examples and non-examples with hydrogen bonding today. It could even be different places on the same big molecule. If after A it reached around and eventually bonded to B in the same molecule, you could have hydrogen bonds within a molecule even, if the molecule were big enough. So you look for NO or F bonded to hydrogen, and then another NO or F with a lone pair, like B over here. That's where you get hydrogen bonding. Now, hydrogen bonding is pretty important for a couple of reasons. We notice, while it's failing to scroll, that the energy of hydrogen bonds is in the dozens of kilojoules per mole. This computer's making me nervous because it was working fine earlier, and now it's just being a little bonkers. I knew this would happen. They got the old computer back finally. I waited as long as I could. They got the old computer back, and so now this is it. And so it knows that, and it wants to mess around with us. But here's is this a figure? This is a figure. 12.15 as it it'll probably scroll for another hour as it just decides what it's doing. It's not an outright graph because the x-axis is not really a quantitative thing. It's a category. It's just what period. But it's showing the boiling points of the hydrogen compounds of different elements by period. So, for example, the second period, we're talking about carbon, nitrogen, oxygen, fluorine. The third period would be the elements below those. So let's look at the carbon group here. The lines connect the ones that are in the same group. So group 4A, methane has a low boiling point. It's a nonpolar molecule. We'll deal with nonpolar molecules very shortly. And we see that the analogs to those, to methane, with a silicon central atom or germanium or so forth, the boiling points increase pretty predictably. Again, it's not a line that you could really literally take a slope of because this is not a variable. It's a continuous numerical thing here. It's just bins. But if we plotted it for the other groups, the boiling points of the hydrogen compounds, look at group 6A, where oxygen is. Hydrogen telluride boils at this temperature, and hydrogen selenide, hydrogen sulfide. You could extrapolate what water's boiling point would be, and it should be down here around, 90 below 0 Celsius, but it's not, thank goodness, right? If water boiled at 90 degrees below 0 Celsius, we would not be here to talk about it, right? Because there would be no solid or liquid water on Earth. It would all be a gas. There wouldn't be solid ice caps or ice cubes for your drink, or liquid oceans, rivers, lakes, bodily fluids, precipitation, etc., right? It would all be a gas. So why is the boiling point of water way up there at 100, where it's extrapolated down to be like at minus 100? Hydrogen bonding, right? Hydrogen bonding is a very significant intermolecular force, especially when you compare to other similarly sized molecules. And that's the disclaimer, is that, if you have differently sized molecules, you have to consider things other than just, does it have hydrogen bonding or not? You got to consider the size. What are the other two of the three outliers in the graph? Ammonia, hydrogen fluoride, what do they have as pure substances? Also hydrogen bonding. So that's a pretty important effect. These three substances with the hydrogen bonding have boiling points that are way higher than you'd predict based on their molecular weight and other properties, their size. So hydrogen bonding is pretty important. We wouldn't be here to talk about it. We wouldn't have liquid water without hydrogen bonding, or solid water. And if there weren't liquid water, how would we have Diet Mountain Dew? So, praise be. Now, that was one good thing in New Orleans. The room had a fridge, and there was a CVS and a Walgreens, and there was a sale. So I was doing really good on that. Okay, now we'll get back to that. This is not only just for drinking. This is also used in examples. Now, the other thing to notice about the hydrogen bonding is the energy of the hydrogen bonds on average is dozens of kilojoules per mole, a few dozen kilojoules per mole, which is important. If you compare that to other intermolecular forces, including ones we haven't yet talked about on the table, it's generally more, right? Many of them are less than 10 kilojoules per mole. Ionic and covalent bonds are in the hundreds of kilojoules per mole. So this kind of hits a sweet spot, energy-wise, that we might want to have if we wanted to stick a couple of molecules or parts of molecules to each other strong enough that they stick, but not so strong that we can't get them apart. It kind of hits a sweet spot energy-wise, and one example of where we would like to be in that sweet spot, if it ever comes up here, this thing is freaking me out because it's, oh dear. Okay, well, here it comes. On the left, at the bottom, now it's going by. There we go. Should have come earlier. It was perfectly fine. I think part of it's maybe trying to record the thing for the people who aren't here. Boy, if you're listening to this later, I'm terribly sorry. Boy, it's skipping and jumping. Adjust your vertical hold. Do not touch your television. There's nothing wrong with it. All right, DNA. Heard of DNA at least? We're not going to deal a lot in this very, very detail of the DNA, but heard of DNA, or watched Jurassic Park and seen, they had the Welcome Center movie about the DNA and the amber and the mosquitoes and so forth, right? And everyone's probably seen at some point some cartoon of DNA with the double helix shape. What makes the strands hold together to each other? Hydrogen bonds. Hydrogen bonds are just the right energy because you've got to be able to duplicate this stuff. You've got to get a transcription complex to go along and make another copy. So you have to be able, essentially, sort of at the molecular level, to unzip this. If it was covalent bonding, that would be too much energy to break covalent bonds all the way up that. It would just be too energetic as far as the energy you need. And weak intermolecular forces, like as we'll talk about dispersion forces and things, probably wouldn't be strong enough to hold this together. Hydrogen bonds are just right. Again, if you ever saw Jurassic Park, makes me feel old. That was 25 years ago. Gosh, wow. I remember when it came out. There's, near the end of the movie, the dinosaurs are running. They're in the kitchen. They're in the visitor center. They're everywhere. And one of them is standing, blocking the screen, and projected on the dinosaur are these A, C, T, and G letters from one of the projectors in the visitor center of Jurassic Park. If you've ever seen A and T and C and G as letters they use in DNA, the A's and T's go together. U if it's RNA. The A and T go together, C and G go together, and that stands for the bases which, they're bases, literally bases in the acid-base sense. They have nitrogen atoms with lone pairs. But the base pairs, A and T or C and G, line up just right that the hydrogen bonds, those are hydrogen bonds, the red ... they line up just right if you have A and T, but they don't line up if you have, say, A and C. They don't line up. And so that's why the base pairs are what they are. One base complements the other, because hydrogen bonds can form between the O or N on one side and the hydrogen that's bonded to N or O on the other side. And it's really elegant. It's really kind of nice. So another reason why, if not for hydrogen bonding, we wouldn't be here. Not just we, the humans, but basically anything with DNA, which is pretty much everything alive, wouldn't be around if we didn't have hydrogen bonds to hold the strands of DNA together. Makes for an easy exam question if you know it's coming. Which kind of attraction holds the complementary strands of DNA together? Covalent bonds, ionic bonds, hydrogen bonds, this, that, something else. Now you know, because it's Ellen's 12 days of exam question giveaways continuing. So that figures from Chapter 15. We don't do all of Chapter 15. We pick the greatest hits from Chapter 15. That's mostly organic chemistry. The organic chemistry people generally ask that we try to leave the teaching organic to them if we can help it. I'm going to try closing this and seeing if it will do better if I reopen it. The thing is like pulsing there. It's like it's ready to reach out and grab me or something. Now it doesn't want to close. Okay. All right. I'm just going to try. If I open the document again, will it do any better? It probably won't. I probably need to stop the recording of the thing. Standard quality. It's not like we're doing it at fancy, Steven Spielberg quality or something. So still got that pulsation to it. I'm not sure. Well, I'll stop the recording if we have to. But so hydrogen bonds are pretty important. Oh, come on. Oh well. Now, let's pick a molecule here. Let me see if I can get it to do it. Okay. I'm going to draw a Lewis structure of methylene fluoride. Not intending to show the shape here. Okay, methylene. It's CH2F2, difluoromethane, if you like, or however you like to name it. If you had a pure sample of liquid methylene fluoride, would there be hydrogen bonds between the molecules? That's the structure. That's a Lewis structure. It's actually tetrahedral, right? 4 bonds to carbons, tetrahedral, 109, sp3, all that good stuff. Main thing is, that's the bonding. That's what the structure is to make it unambiguous. Would there be hydrogen bonds between the molecules of methylene fluoride in a sample of liquid CH2F2? It's got hydrogen. It's got fluorine. It must have hydrogen bonding, right? Seems like there must be a trick, right? Yes, there's a trick. No hydrogen bonding there. Why? The answer is no. The question is why? Why no hydrogen bonding? The hydrogen has to be bonded to the NO or F. Here the hydrogens are bonded to carbon. So are the Fs. Not that matters, but the H is not bonded to F, and that does matter. If the H were bonded to an F, O, or N, then yes, there'd be hydrogen bonding. FH bonds are not that common. The only common substance that has an FH bond is hydrogen fluoride, because it obeys the octet rule with a single bond to fluorine. So it's hard to get hydrogen with a bond to fluorine that's bonded to something else. There are some oddball things, but they're not very common. Nitrogen and oxygen, on the other hand, very common. Most hydrogen bonds involve N or O. There aren't that many with F because F doesn't form many bonds. But all the amines, those weak bases called amines, ammonia, water, alcohols, sugars, lots of things with OH bonds can form hydrogen bonds. So this doesn't have the fluorine hydrogen bond that you would need to do that. And by the way, I mentioned liquid CH2F2. Not that it's totally restricted to that, but it does bring up a point that people argue sometimes, that if we're talking about a gaseous sample of a compound and we start talking about the hydrogen bonds between the molecules in the gas phase, that kind of doesn't go with what we know about a gas, right? A gas is supposed to have the molecules in constant motion, bouncing off each other. KMT, kinetic molecular theory, says no attractions between the molecules are very important. And so to then start talking about the attractions between the molecules when we know that they're not very important, that's why we usually stick to things in the liquid or solid state if we can help it when we're talking about this. Because in the gas phase, there shouldn't be appreciable effect by the intermolecular forces. They do exist, but only at very close range. They're not important in the gas phase as much as people would conclude if we didn't restrict it. So that's why it seems like oddly particular to say in a sample of liquid, but it's important. So those three in the table that are at the top there, whenever it decides to stop moving, they involve polar molecules. Ion dipole, 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 and hydrogen bonding involve polar molecules. The next three need not involve polar molecules. They may involve polar molecules. I'm not saying they don't, but they don't have to. The first two, ion-induced dipole and dipole-induced dipole. The induced refers to the idea that you have a nonpolar molecule standing by, and something with a distribution of charge comes near it. The first one, the ion-induced dipole. Let's say they have an example here of O2 with a ferrous ion getting near it. I don't know if this was like a ferrous ion in liquid O2. I'm not sure if this were in the gas phase. I'm not sure, I'm trying to avoid gases, but whatever. O2, it's nonpolar, right? Two oxygens, they're both the same electronegativity. It's diatomic, bond's nonpolar. The ferrous ion is a +2 charge. The analogy for this is something like, let's say you have a 7th grade dance with couples of boys and girls, and they're all, grudgingly dancing with their date. And then Justin Timberlake pulls up in a limo outside. I couldn't think of who to use earlier, and I couldn't think who was popular, but he's popular enough, I guess, with people, right? Because I used to think of like the Spice Girls or something, but no one has any idea who they are anyway. Or the Backstreet Boys or NSYNC, or they were very popular around the same time as each other. So let's say JT pulls up outside in a limo, and the girls get very excited and run to the windows and doors, and they're screaming and everything. The boys couldn't care less, and right then the principal comes in with a camera to take a picture for the PTA newsletter, and the girls are over here and the boys are over here. It would be like this picture right here, where the ferrous ion would be like Justin Timberlake, and this oxygen molecule, the electron distribution is the girls running over, they're attracted to Justin Timberlake, and the boys don't care, and there's a separation of charge where the electrons want to get near the cation momentarily. Now, what happens when the ion drifts away? O2 goes back to looking nonpolar again, and it would go back to being a purple circular shape that's hard to depict. See, they never do show something that's nonpolar here. They always manage to have it, induced. So right at that moment, the ferrous ion has induced the O2 into looking polar. It's not polar overall permanently, right? It has a zero net dipole permanently, but it has a temporary polarity just for that fleeting moment that those are near each other. So if this were a Snapchat or a picture on a camera or something, it would look polar, and then it goes away. So that's the analogy. It seems silly, but it's how else are we going to get Justin Timberlake mentioned in class? You can induce a dipole with another polar molecule. HCl is polar, Cl2 is not. But if HCl comes close enough to Cl2, it can make Cl2 look polar. In this case, the negative end of the HCl molecule, the chlorine, makes the electrons in Cl2 say, ew, negative charge, let's get away from that. And right then at that moment, Cl2 looks polar. It's not polar permanently, just temporarily, so it's an induced dipole. These induced dipole forces are weak. Maybe a dozen kilojoules per mole tops, because they're temporary. Now, there's more than two molecules in a sample, right? You'd be talking about mole quantities. This can be passed around from molecule to molecule, and so it adds up. But they're relatively weak. But they are important, they do exist, and we need them to understand stuff in the next chapter. So there we have them. The last item on the list is called dispersion forces, sometimes called London dispersion forces or London forces. Usually dispersion's the name we use. A wordy name for this could be induced dipole forces. Okay, if you think about it for a second. Let's say you have these two in the example here. F2, molecule of F2. Has 18 electrons, right? There are 9 electrons in a fluorine atom. 2 fluorines bonded to each other, total of 18 electrons in the molecule. Now, the F2 molecule should be nonpolar, right? It doesn't matter that fluorine's very electronegative. It's bonded to another fluorine, which is also the same electronegativity. So the FF bond is nonpolar. The molecule is nonpolar. Now, 18 electrons in a fluorine molecule, it's nonpolar, so on average, there's 9 on each side of the molecule. Imagine if you had an imaginary line through the middle of the molecule. Being nonpolar, what that means is on average, there's 9 electrons on the left and 9 on the right, most of the time. Could there be 10 and 8? That could happen, right? It's probability, it's orbitals. Electrons are flying around. There could be 10 over here and 8 over there for a moment. And then what would it look like if you took a picture of that? It would look polar, right? It would have more electrons on one side than the other. It would be partially negative over here, partially positive over there. It would look polar. What would the fluorine molecule next to it do in response? It would shift its cloud of electrons to get more electrons near the positive end of the first fluorine molecule and so forth. So thanks to the idea that electrons are flying around in these orbitals, you could polarize your electron cloud, have more on one side than the other, look polar temporarily, make the molecule next door look polar temporarily, and pass it along through the whole sample of fluorine. Now, that's the idea of this induced dipole force. Right? It is dipoles inducing each other, passing along through the whole sample. These are often pretty weak. They can be as much as 0.05 kilojoules. It's only 50 joules per mole, but up to 40. And if you look at the energies here, that 40 overlaps all the others, right? It could be as big as hydrogen bonding. It could be as big as ion dipole force. Dispersion forces may be relatively strong. And this is an important thing. This is another important thing about intermolecular forces. It's not well understood. It's not well taught a lot of the times. I know people who they will take a figure like this, or there's one in chapter 13 that summarizes these as well. I know someone who crosses out the 40 in their PowerPoint. They cover it over with a white square and then type a number 2 there so that it is less than the others. And that is wrong. I don't like to call people out often on things like that, but they do that because they want to be able to say in class, dispersion forces are the weakest. They are weaker than all the others, but that's not necessarily the case. It's not always the case. Consider iodine, I2. How many electrons are there in an iodine molecule? Let's see. Where's iodine? It's number 53. That's in it's 3 below fluorine. So how many electrons total in an I2 molecule? 106, right? So it's a nonpolar molecule. It has 0 net dipole moment as a permanent dipole because it's a bond between 2 identical atoms. So it's nonpolar. So 106 electrons flying around in this molecule. Is there a chance that instead of 53 and 53, if you divided it in half, it might be 54 and 52? That's certainly possible. Or maybe 55 and 51? That's not outrageous either, right? Maybe 56 and 50. That's not outrageous. There are many more ways to polarize that electron cloud in an I2 molecule with that many electrons, right? The more electrons there are, the easier it is to polarize the smushy cloud of electrons than if it's a little tiny molecule. So I2, being a big molecule, it's more easily polarizable, and we would expect the dispersion forces to be stronger because it's easier to polarize the molecule. And the data bear that out. What state of matter is iodine found in? If you have a pure sample of iodine at room temperature, atmospheric pressure, you don't encounter it a lot, necessarily. It happens to be a solid. These periodic tables, it's hard to tell sometimes the difference in the way. The black ones, if you, I think we've mentioned this before, but the black type means it's a solid. The red means it's a gas. The blue means it's a liquid, and there's only 2 that are printed in blue. It's hard to tell the dark blue from the black. But bromine is a liquid, and so is mercury. But if you see those periodic tables, it's easier to tell in the lab if you have a chem lab. These are the same on the wall in the labs. It's easier to see the dark blue versus black ink. But this figure here, as it goes by at its own pace, the italic number is molar mass, and then the bold-faced italic number is the boiling point in Kelvin. And we see fluorine has a molar mass of 38. It's a relatively light molecule. Boiling point for F2, 85 Kelvin, nice and cold, close to that of liquid nitrogen. It's actually a little more than liquid nitrogen because fluorine is a little bigger molecule, has more electrons, so it actually has a little more in dispersion forces. Look at iodine. Molar mass 253.8, boiling point 458. Yeah, I mean, we know the boiling point's above room temperature. Actually, and so is the melting point even. It's a solid. Bromine's in the middle, right? Its boiling point is above 298. It's a liquid. Why the trend? Why do the boiling points go up when you go fluorine, chlorine, bromine, iodine? Because of increasing dispersion forces. Because they are bigger molecules with a bigger cloud of electrons. It's easier to polarize. So think about this. Iodine's a solid at room temperature and atmospheric pressure. Water's a liquid. Who has the bigger, stronger, more important intermolecular forces? Iodine or water? Which one has bigger, stronger intermolecular forces overall? Iodine's a solid. It must be the iodine. Think about it. The iodine's a solid. The forces between the molecules of iodine are strong enough that you need to go above room temperature just to melt it. Never mind boil it. Water, even though it has hydrogen bonding, you put in the same amount of energy. At room temperature, you put a certain amount of energy in, and it's a liquid. Now people say, but wait a minute, I thought hydrogen bonds were strong and dispersion forces were weak. And this is where I don't like this person I know who isn't in this building, thank goodness, who I've seen change the value on the table from 40 to 2 because they like to teach that the dispersion forces are always the weakest intermolecular force. They're not. The dispersion forces in iodine are stronger than the hydrogen bonds in water. They have to be. Iodine's a solid. Now, why can that be? Consider the sizes of the molecules. Consider the mass. What's iodine there? 253.8. Ooh, for a molar mass in grams per mole. What's water? 18. Okay. It's a lot smaller molecule. The number of electrons. How many electrons total in a water molecule? 10. Total, not just valence electrons, all the electrons, including core electrons, is 10. Iodine, 106. Right? Way more polarizable molecule, way easier to polarize that electron cloud, stronger intermolecular forces. So dispersion forces are not weakest always. If you're comparing like-size molecules, then dispersion forces would be weaker than dipole-dipole forces, weaker than hydrogen bonds. When you're comparing totally different size molecules, and say, well, wait a minute, oxygen, water has 3 atoms and I2 has 2 atoms. Yeah, but consider the size of the atoms. Don't count atoms. Count electrons. Count the electrons. That's what goes into the polarizability. I2 is a bigger cloud of electrons, much, much bigger. So that's a huge discrepancy in the dispersion forces. Same with the noble gases. Xenon has a relatively warm boiling point at 165 Kelvin. That's still cold. But compare it to the other halogens as you go up the group. As the atoms gets, liquid xenon. It's a nonpolar substance, right? It's atomic. So it's nonpolar by default. There are no bonds. Neon's boiling point, only 27 Kelvin. Go up to helium. Eventually we'll get there. Helium's boiling point is just a notch over 4 Kelvin. That's cold. And why is it so cold? It's an atomic substance with 2 electrons. How are you going to polarize helium atoms? Basically, the only way to do that is to have both electrons on one side of the nucleus. Is that possible? Yes. Does it happen a lot? No. I mean, it's possible if you have 2 electrons in one s orbital to happen, but they have extra sig figs on there mainly so that they didn't just both say 4. Because that would look like maybe it was a typo, They're both 4? Isn't that weird? Gee, it's 4 grams per mole. It's about 4 Kelvin. So they They kept extra sig figs. But that is the same thing with dispersion forces. The dispersion forces in helium are very weak because it's a very tiny atom. And it's atomic. There are no bonds involved in that substance. So dispersion forces are not always the weakest. We don't want people to think that they're always the very, very weakest. They are present in everything. Everything has dispersion forces. There are dispersion forces between liquid water molecules and liquid water, but they're very weak compared to the hydrogen bonds. So you don't care about the dispersion forces. What if you have liquid xenon? Then all you have is dispersion forces. So if it's nonpolar, all it's got is dispersion forces. If it's polar, then it's going to have dipole forces as well as dispersion, and usually the dipole forces are stronger. But if we're talking about a big molecule, the dispersion forces can be important. So that's important for us to understand that for large molecules, dispersion forces can represent a significant fraction of the total intermolecular forces. They might be the most important, even though you might think something else could be. Dispersion forces are pretty important. Also, the shape of the molecule might come into play with dispersion forces. I have to reboot this bad boy again here. It's happened I don't know what's going on. Oh well. It knows it doesn't have its partner nearby anymore. The old computer's gone, so it's sad. These two cartoons here are both of molecules with formula, C3, sure, C5H12. These are a pair of things called isomers. We'll see that term again in a week and a half or 2 weeks, technically defined, maybe sooner. I can't remember. Depends which order we do the stuff in. Isomers are molecules with the same formula that have different structures somehow, and there are lots of different ways to accomplish that. You may have seen this in Chem 1 when we're talking about sigma and pi bonding. And then the result that double bonds don't allow rotation that single bonds do, and so you can get isomers with double bonds. That's one place it comes up in Chem 1 near the end of the semester. But we'll deal with isomers in a lot more detail, in disgusting, gory, nauseating detail really soon. But just for now, that's what we call those two. They're both C5H12. The upper molecule here is the so-called straight chain form of C5H12. It's not literally straight, right? If you look at the structure, all those carbons are tetrahedral. They have 4 bonds. They're sp3. The angles are 109. So it's not literally a straight chain. But when they say straight chain, what they mean is no branching. Each carbon is bonded to 2 other carbons, one on either side, except the ones at the end. And you could have a very long straight chain with 20, 30 carbons, or a relatively short one like this. But that's a so-called straight chain. This N-pentane, the pentane name the pent comes from the fact that there are 5 carbons. The ane has to do with the fact that there are only single bonds in the hydrocarbon. Has a boiling point of 36.1 degrees Celsius. It's a liquid at room temperature. The dispersion forces can act along where the molecules might bump into each other, which is a relatively decent area. The molecule being a straight chain form, the chain can bend, the chain can flop a little, but it's kind of a tubular Tylenol caplet shape. And they can meet each other at more than one location. Compare that to the other structure. And by the way, there is a third as well. There actually is a third possible C5H12 that's not involved here. The other C5H12 that we have possible here is 1 carbon in the middle, bonded to all the other carbons. And that one is, the nickname is neopentane, and that is to reflect that it is a 5-carbon hydrocarbon, so it's named as a pentane. The systematic naming of this would not call it a pentane. They use the longest chain, and this would be named as a branched propane, where propane is 3-carbon chain. So it would be a dimethyl propane, but that doesn't easily indicate that it has 5 carbons. So the common name neopentane is very frequent to see. The middle carbon is tetrahedral. Each of the carbons attached to that has 3 hydrogens on it in a tetrahedral geometry as well. The molecule overall, especially if it's in motion, kind of looks spherical-ish because it's that tetrahedron circle, rotating in space. And that 2 spherical molecules, they can only make contact in a very small region, right? If they were literally spherical, they'd only be able to touch at a point. They're not perfectly spherical, so we might give them a little bit of a break. But the important thing is that These molecules are both nonpolar. CC bonds are nonpolar. CH bonds are nearly nonpolar. And the geometries of these molecules is such that any polarity there might be to the CH bonds kind of cancels out with other CH bonds in the molecule. They're nonpolar. Both of those are nonpolar molecules. And so they only have dispersion forces, and the dispersion forces here can only form in a very limited region in space. So they're weaker than the other isomer. And they're so weak that the boiling point of neopentane, or a dimethylpropane if you like, 9.5 degrees Celsius, below room temperature. This would be a gas. It would be above its boiling point at room temperature, right? So let's say I had a sample of both mixed together at 0 degrees Celsius. They'd both be liquids there, right, at 0. Beaker full of both liquids at 0 degrees Celsius, and let it sit and heat up in the room. Hopefully with a fume hood over it. Bring it in the lab and get one of those crazy snorkel hood things over it and everything. Neopentane would boil away, and the N-pentane would not, because room temperature is in between, right? So that's kind of interesting that room temperature is actually in between those two. But the N-pentane would not boil off, and the neopentane would. And that's because of the shapes of the molecules making the dispersion forces stronger in the straight-chain molecule. So shape has something to do with it as well. They have the same molar mass, right? They're both C5H12. They have the same molar mass. They have the same number of electrons. They're both nonpolar, but there's something different about those intermolecular forces, and it's the shape. The shape of the molecule means the same kinds of forces have fewer places to act in the neopentane. So shape's important. Shape is an important aspect of the molecules as well. So there's a lot going on with the intermolecular forces, but it's good to be able to recognize what kind of intermolecular force is involved in which sample, because there's lots of different kinds. So that's in chapter 12, and then there's some places, some folks who do chapter 12. They try to squeeze chapter 12 in at the end of Chem 1, and then they start Chem 2 with chapter 13, and people have forgotten chapter 12 over the holidays, and so the beginning of chapter 13 actually has the intermolecular forces repeated, basically. So if you're reading chapter 13, you might say, gee, this is the same stuff as in chapter 12 about intermolecular forces, and that is correct, because some people do it, different semesters or something for whatever reason. But let's use what we know about the intermolecular forces to deal with mixtures now. Okay, chapter 13 deals in solutions. We yanked a little bit of chapter 13 out earlier, right near the beginning with molarity and molality and stuff. So we'd have the units of concentration to use with equilibrium and stuff. But now we can talk about solutions as a concept, why they form, how they form, a little bit. So, does something dissolve in something else? It depends on the intermolecular forces. It depends on the kinds of bonds, the intermolecular forces. If the driving forces are favorable, then we know we get a spontaneous process. And this is where, it works out well, actually, that we know something. We've heard something about delta H and delta S and delta G and stuff. We can actually use that a little bit here, because in chapter 13, they actually talk about entropy and stuff without defining it very carefully until 7 chapters later. So we were ahead of the game on that. If the driving forces, namely that is enthalpy and entropy, combine to give a favorable free energy change, then a solution will form. If it's not favorable, it won't. So we can model the solution process as if it were 3 steps. Now, this is a model. It is not literally 3 separate steps. The reason for 3 steps is to use Hess's law. Right? Because if you can break it up into 3 mythical steps that you know the enthalpies of, then you can use Hess's law to do the enthalpy. It's not actually 3 separate steps. The 3 steps are, you separate the solute particles. Let's say I got like sugar dissolving in water. So step 1 would be separate the sugar molecules from each other to make room for the water. A sugar has lots of hydrogen bonding. Sugars have lots of OH groups, which can form hydrogen bonds with oxygens. I also have oxygens, double-bonded oxygens in them. Depends how you draw your sugar, if you like to draw it as a ring or as a straight chain or this or that, but there's hydrogen bonding everywhere. Okay, so breaking the hydrogen bonds is endothermic. It takes energy to break the hydrogen bonds. You have to separate the water molecules from each other to make room for the sugar. That's sort of the opposite, right? Separate the sugar to make room for the water, separate the water to make room for the sugar. Also endothermic. In the case of water, that's also hydrogen bonding. You get a break. So the first two steps are always endothermic. It doesn't matter what kind of forces we're talking about. They could be dipole-dipole, they could be hydrogen bonding, they could be dispersion forces. Doesn't matter. Whatever they are, they are. Breaking them's endothermic. The third step is always exothermic, when you mix the two substances together and you make new intermolecular forces. So in the case of sugar and water, we're going to make new hydrogen bonds between the sugar molecules and the water molecules. Primarily hydrogen bonds because of the OH groups that are present in both substances. But we could also have dipole-dipole forces involved. If we have the waters interacting with parts of a molecule, let's say it's not a sugar, but some molecule that's polar but doesn't have hydrogen bonding, then we would have dipole-dipole involving water. So whatever the new forces are, ion dipole, dipole-dipole, hydrogen bonding, new dispersion forces, whatever they are, forming those is exothermic. Just like ionic or covalent bonds, when you form these forces of attraction, that's exothermic. Just like forming a covalent bond is exothermic. So the third step's always exo, the first two are always endo, and when you add it up, the total could be either positive or negative because it depends on how big the enthalpies of the three steps themselves are, right? I mean, if the first two are really, really endothermic, and the third step is only kind of exothermic, then it's going to add up positive. But if the first two are only kind of endothermic, and the third step is really, really exothermic, then that's going to add up negative. So the grand total could be positive or negative. It depends on how big each of the three delta H's is in the steps, but we can add them up and figure it out. And that's what the cartoon below is intending to show. Yeah, here we go. So if it'll... Poor thing. I know your buddy is gone. I'm sorry. But it had a good life. They give you a receipt when you hand in your old computer saying that you handed it in so they can't worry, bother you about it later. And it said on the form, it said disposition, scrap. Aw, poor thing. So this thing probably saw that and feels bad, I think. So this is figure 13.14. If you already have the textbook electronically or in hard copies, you don't have to draw it yourself in your notes or something. But as we see, the first two steps are always endothermic, separating the solute and the solvent. Those are always endothermic. It's the third step that's always exothermic, delta H mix, that's always exo. But the grand total could be endo or exo, depending on the relative quantities that are involved. And that's okay. Some substances, when we dissolve them, it's exo, some it's endothermic. And we know that. But if it's too endothermic, that's not going to help, right? Endothermic, exothermic is only one part of spontaneity, right? Now, in the case of solution formation, exothermic helps. If it's exothermic, it'll probably occur. If it's endothermic, it's going to need help. But we know there are two things. There are two driving forces to every process, enthalpy and entropy. So let's look at case number one here, where we're talking about enthalpy in the driver's seat mainly. Okay. Now, for whatever reason, whenever they do this in any textbook, it doesn't matter which textbook, they talk about the three steps, then immediately they start talking about ionic compounds, and they do it in two steps. Who knows why? And I know why they do it is because you recall lattice energy? Recall in Chapter 9, lattice energy, it's the energy associated with taking an ionic crystal in the solid state and turning it into gaseous ions. You might recall that's in Chapter 9. You might recall that lattice energy is a measure that's related to the strengths of ionic bonds. The larger the lattice energy, the stronger the ionic bonds are. So they use lattice energy in this. So that's kind of like delta H solute in the three-step process. The other two steps, delta H solvent and delta H mix, are combined into something on here that says delta H hydration. The enthalpy of hydration of the ions. That's the enthalpy involved in taking the gas phase ions and making them aqueous ions. And implicit in that is the water molecules separating to surround them. So the delta H hydration is kind of like steps 2 and 3 together. So it's the same overall thing. But you can measure the heat of hydration, not literally measure, but you can calculate it, just like you can lattice energy. You can't actually measure lattice energy. What are you going to do? Like get a coffee cup and put sodium chloride in it and convert it to gaseous ions? Forget it. Right? You can't measure that directly. But you can use Hess's law to get the lattice energies, and they're in data sources already. So same with hydration energies. They're data that we have. So it's the same 3 steps. It's just that steps 2 and 3 are combined as one here. Okay, the same 3 steps. Don't sweat it. So think about salt, ordinary table salt, NaCl. That's the salt known as salt, right? If someone's talking about salt, they're probably talking sodium chloride. We know better, right, that salt is a category of things. But if someone dissolves NaCl in water, say you have a glass of water, you could do this at dinner. Find a salt shaker, put salt in the water. Does it get noticeably hot or cold? Ever notice it? If you ever did that, you try it later. You don't really notice it get hot or cold. It turns out the enthalpy of that process is pretty much flat. It says here 3.9 kilojoules per mole. It's endothermic, but barely. It's not endothermic enough to even really notice. It's virtually zero. And that's fine. Turns out that the lattice energy of NaCl and the heat of hydration of the ions are about the same. So why would that solution form? It's slightly endothermic. It's got to take in energy. Something else must be involved, but the enthalpy is not standing in the way, right? The key here is that enthalpy is not a problem. It's not like the enthalpy is way too big. NaOH, sodium hydroxide. I think they still do this in the lab. I don't know. I think it's the acid-base titrations experiment in the qual lab. We used to have a step where you'd make a sodium hydroxide solution. I can't remember if it was that one or the one in Chem 1. Maybe it was the Chem 1 one. You'd make a sodium hydroxide solution to determine the concentration of, and then you use that later. And they'd say, take so much of the NaOH, so many pellets or whatever, dissolve it in water. I can't remember which experiment it is, but I know there's one experiment. We used to do this anyway. And it was a little dangerous because NaOH, when it dissolves in water, it gives off a lot of heat. And people would hold this flask or beaker in their hand, and they'd mix the NaOH into it, and it would get really hot. And then they would, they'd either drop it or tip it over, and it would start one of these Rube Goldberg accidents with 6 people involved. Did I describe that one time? It took 6 people for someone to get concentrated nitric acid on their back. Did I ever describe that? It was a great chain reaction accident. It took 6 people. Very exothermic. The heat of solution of NaOH minus 44 kilojoules per mole. So the solution gets real hot. If you take NaOH and dissolve it in water, it gets hot. Pretty hot. And that's because steps 2 and 3 add up to something so exothermic. And step 3, that's the exothermic one, right? Step 3 is so exothermic that it way overcomes the enthalpies of steps 1 and 2, where step 2 is part of the down arrow. 2 and 3 have been added together already. But step 1 is overcome by step 3. And so it's exothermic overall. Now, have you ever used one of those cold packs that you smack it or you break it in your hand and squish, 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 and it gets cold? Ever see those? Someone gets, they twist their ankle or this or that or something, and you want to put ice on it, but you don't have ice, but you break one of those cold packs. Usually they have ammonium nitrate or something like that in them. Solid ammonium nitrate, you dissolve it in water. It's endothermic to the tune of 25 kilojoules per mole. Nice and endothermic. Now, it's not endothermic enough that it won't happen, but endothermic isn't good for spontaneous, right? We know this is one advantage of having already done thermodynamics, is we know that enthalpy is just one part of spontaneity. The other part is entropy change. And if the enthalpy is positive, if this is going to be a spontaneous process, dissolving ammonium nitrate in water, then what do we know about delta S here at room temperature? Delta S is going to have to also be positive, right? Because that's the only way that delta G can come out negative. And we know the stuff dissolves, so it has to be negative, which means delta S has to be positive. Does that go with what we know about the reaction, the process? The entropy of solid ammonium nitrate versus dissolved ammonium nitrate. Which has the higher entropy? The dissolved, right? The ions are free to move. They're aqueous. They're moving around. In the solid state, they're just kind of sitting there vibrating in a crystal. So yeah, delta S is positive for this process of dissolving. It is for NaCl as well. That's what saves us on NaCl. So yeah, enthalpy is the biggie here because even if it's endothermic, there's enough energy in the surroundings to make the reaction happen. But we see that even though enthalpy is involved, entropy is as well. and they do mention this in Chapter 13, they mention entropy, but they pay lip service to it and say, in Chapter 20, you'll learn more about this. And that's where, it's good that we've actually talked about it. Because now we know what it is. Caller, turn down your radio. So, okay, enthalpy and entropy both have roles to play. The key is that even for the endothermic one, it's not so endothermic that it won't happen, right? The entropy change, delta S, is enough to overcome the enthalpy change, delta H, which is good. That means it'll dissolve. If we're too endothermic, it might not dissolve, and we'll figure that out. Okay, so, all right, enthalpy has a role to play. If it's exothermic or not very endothermic, then we'll be okay. Now, what if the enthalpy change is not a major player? Like NaCl, it's not a major player. It's about 0. What if I had hexane and octane? Hexane is C6H14. Octane is C8H18. Let's say for simplicity that we're just dealing with the straight chain forms of those substances. It doesn't really matter. You can buy a bottle of probably at chem stores. They sell this to, not to everybody, but to, to other departments or research labs or something. You can buy a bottle of hexanes, plural. And it says hexanes, plural, because it's literally a mixture of isomers. So there will be straight chain C6H14, and there will be branched ones. There will be ones that are shorter chains with branches as well. And they're all mixed together, and it's fine. But let's assume we're dealing with pure straight chain hexane, N-hexane, and N-octane. Pure substances, they're nonpolar. They only have CC single bonds and CH single bonds in them. Those bonds are polar, are nonpolar or nearly nonpolar, and the overall structure of the molecules makes them nonpolar. Let's say I had a tank with a divider in the middle. Hexane on one side, octane on the other, and I remove the divider. Now, the substances are going to mix with each other and form a solution, a homogeneous mixture. Solution is just a one-word name for a homogeneous mixture. Going to completely dissolve one in the other. Why do they dissolve one in the other? Is it enthalpy? I mean, what kind of forces are there between C6H14 molecules? Dispersion forces, right? It's nonpolar. There are no polar molecules there. Only dispersion forces. How about octane? Pure octane. Forces there? Just dispersion forces, right? So breaking up the molecules to make room for the others involves breaking dispersion forces, which are not the strongest things in the world, but they're something. Okay, fine. Then we're going to make new intermolecular forces. We're going to make, let's say we have a mole of hexane and a mole of octane. We're going to break a mole's worth of dispersion forces in each. Then we're going to mix. So we're going to make 2 moles worth of new dispersion forces between these nonpolar molecules. So delta H mix is going to be about the same in the reverse direction as the sum of the first two. Because, originally we had hexane and hexane dispersion and octane dispersion forces. Are the dispersion forces that you make with a hexane and an octane that much different? Not really. They're virtually the same. So you make new dispersion forces that are about the same in energy as the old dispersion forces for an enthalpy of solution that is about 0. Why does the solution form then? And why would that mixture form? If the enthalpy of solution is 0, it's not enthalpy. It's got to be the entropy, right? If you have delta H minus T delta S and delta H is 0 and you need the grand total to be negative, then your delta S has got to be the positive part. And we know it is, right? How many ways can you disperse the energy into the motions of mixed particles as opposed to a pure substance? A lot more ways with the mixture. So the entropy increases when you form that mixture. That drives the process to be spontaneous. So entropy is the driver here, especially when you have mixtures of covalent compounds. When you have hexane and octane or other things like that are alike in intermolecular forces in the pure state and alike with each other in a mixture as well. Enthalpy is not the driver there. Entropy, delta S, is. So, okay, that's fine. We can do that. Now let's take a solute from case 1 and a solvent from case 2 and mix those together. So let's take the NaCl from the first case and the hexane from the second case, and consider mixing them with each other. So you got to separate the hexanes to make room for the salt. So that is dispersion forces to get broken up. And then you got to separate the salt particles. That's ionic bonds. That's a killer. Right? There's lattice energy involved. That's like hundreds of kilojoules per mole. That's going to be a big problem. When you mix the two together, when you mix the ions from the salt with the hexane, what intermolecular forces do you form? If you have an ion and a nonpolar molecule, that is ion-induced dipole forces, right? That's Justin Timberlake pulling up outside the dance. So the sodium ion is going to be surrounded by hexanes, and the hexanes' electrons are going to say, ooh, positive charge, let's get near that. And the chloride ion, the electrons in a hexane are going to say, ew, negative charge, let's get away from that. And so you're going to form, okay, ion-induced dipole forces are going to be formed. How strong are ion-induced dipole forces? It's hard to scroll, so let's see if we can remember. The dispersion forces are maybe a dozen kilojoules per mole. Ion-induced dipole forces were less than a dozen. Lattice energy of NaCl, like 700-800. Uh-oh. This is a killer, right? This is where we need one of these capacitors here, right? And it's not a capacitor, right? But we have to break the arrow, it's so tall, compared to the other arrows, in order to fit it. So delta H solvent is, a dozen kilojoules. This is 700-800. And then this is, minus a dozen, tops. Ouch. Delta H overall, way, way huge. Greater than 0. Anytime they get a double greater than, that means, stupid huge. Too endothermic to bother trying, right? It's far too endothermic. If we consider delta H minus T delta S, delta H is going to be, hundreds and hundreds of kilojoules. Yeah, the delta S is positive in the mixture, the theoretical mixture. Yeah, delta S will be positive when you dissolve the ions into the hexane. But it's not positive enough when you multiply by T and change the sign to make the total negative for a spontaneous process. That delta H is just too huge. And so the solution doesn't form. And so ionic compounds like NaCl don't dissolve in nonpolar solvents like a hexane or an octane. It would have been the same with octane. It wouldn't have mattered. People say, what about octane? Maybe that would work. No, it wouldn't work. Neither would heptane. This just wouldn't work. So this sort of shows that, okay, we had a nonpolar thing dissolving in a nonpolar thing. We had ionic compounds dissolving in a polar solvent, water, but the nonpolar solvent didn't dissolve the polar or ionic substance. The moral of the story, generally a rule of thumb, the statement that you hear people say, that you can teach your parrot, it loses all meaning. Like dissolves like, is the summary of this. Like dissolves like, want a cracker. And I wonder what happened to the parrot from the Activia commercials a few years ago. I should bring him in, teach him this. It loses all meaning. People hear like dissolves like, and they have no idea what it means anymore. It's like big bucks, no whammies, like dissolves like. I don't know what it means. It's not a perfect rule. It's a general rule of thumb that says nonpolar solutes tend to dissolve in nonpolar solvents. Polar or ionic solutes tend to dissolve in polar solvents. But that's tend to. Are there exceptions? Sure, and they're important. Like O2 is nonpolar. Does it dissolve in water? Sure does. Same as CO2. CO2, also a nonpolar molecule, also dissolves in water. We saw it with the bubbling beaker of doom, right? CO2 does dissolve in water, and it's a good thing. Aquatic life appreciates the fact that CO2 and O2 dissolve in water because the plants need the CO2 and the animals underwater need the O2 to get in the gills or whatever so that they can live, right? So those are nonpolar substances that are soluble in water, which is polar, and we need it, okay? So it's not a perfect nothing nonpolar dissolves in water or something. We're not saying that. There are nonpolar things that dissolve in water, and thank goodness, because animal and plant life needs it. But it's a good rule of thumb. So if you use the word like a lot in your sentences when you're speaking, so it's like somebody was saying like dissolves like, and it's like that can be very confusing. So we don't want to get embroiled in that. But So be careful with your like, or it's better if you say you know than like in this case. But like dissolves like is a general thing. It's not perfect. Okay. What affects solubility of things as far as this like dissolves like, and then some other factors as well? Structure affects solubility. Here are two vitamins. The first cartoon here is a Lewis structure drawing of vitamin C. It doesn't have the lone pairs drawn, but that's fine. We know they're there. All the oxygens have two lone pairs. It would be clutter to draw the dots everywhere. That's more Lewis structure. The second cartoon, we've seen that kind of drawing before, I think. Anywhere that there's the end of a line or an intersection or an angle, there's a carbon atom. And then the carbons must have enough bonds to obey the octet rule by adding hydrogens. So, for example, here's an angle here. That means there's a carbon. There are only two sticks drawn, which means there must be two more bonds, two hydrogens. And over on the Lewis structure, there they are, the two hydrogens. So here's a carbon here at that lower right corner. It already has 4 bonds. It doesn't need any hydrogens, and it doesn't have any. So that's how you read those cartoons. If you get a prescription and there's that little piece of very thin paper that's folded over 27 times to fit in the box, and you unfold it and there's a big molecule drawn, and it's one of these line angle structures, that's how you read it. So there's vitamin C as a structure. The other one here is vitamin A1. It's not in steak sauce. Okay, so somebody asks, is that in steak sauce? My dad was always, he would always joke. I said, do you want some gravy on your mashed potatoes? Or the waiter or someone would ask, do you want gravy on your mashed potatoes? Said, oh, a little vitamin G, that would be good. He always, the initials of things became vitamins somehow. So vitamin A1 is not in steak sauce, although it should be. Lots of carbons, lots and lots of carbons actually, not many oxygens in that molecule. Which of those vitamins is more soluble in water, do you think? A or C? More soluble in water. Vitamin A or vitamin C? Think about water. What water has? It's H2O. Which molecule has more things that are, for like dissolves like purposes, that's where structure is involved, is like dissolves like is involved in structure. C? I hear people murmuring C. We're not speaking Spanish suddenly or anything, right? C? My mom got embroiled in a thing like that one time. She was a teacher, and a teacher that worked with her spoke Spanish, and there was a parent came in for a meeting, and the student's parent only spoke Spanish, and the other teacher needed someone to back her up in the meeting, and so she grabbed my mom, and my mom said, I don't know Spanish. And she said, that's all right, just nod and say C when I look at you. And it worked, apparently. The mother was very happy and everything. So I hear people saying C, and I'm afraid that's another sudden Spanish thing going on. Okay, so C. Vitamin C, more soluble in water. What about A? Vitamin A would be more soluble in fats or oils. The main thing there is just a difference in the state of matter. You can have similar compounds. If it's a solid, they call it a fat, and if it's a liquid, they call it an oil. Basically, it's the same kind of greasy molecule, a fat or an oil, just what state is it at room temperature. But vitamin A is more fat-soluble. Vitamin A is a fat-soluble vitamin, and there are others. Vitamin C is a water-soluble vitamin because of like dissolves like. Look at all the places you can form hydrogen bonds on a vitamin C molecule. There's one, there's one, there's one, there's one, there's one, there's one. Right, the O's could form hydrogen bonds with H's on water. The OH's could form hydrogen bonds with the O's on water. I mean, there's tons of places for hydrogen bonding. So vitamin C is very water soluble. If you look at a food label for some kind of juice or something that's got vitamin C in it, and you look at it and it's got 900% of the daily recommended vitamin C or something, where's all the extra vitamin C going to go? You'll excrete it. Right? You can tinkle it out. It's fine. It's water soluble. Now, what if you have way too much vitamin A in your diet? Harder to get rid of because vitamin A is a fat-soluble vitamin thanks to the structure. There's one place to do hydrogen bonding on that molecule over at the end, and otherwise it's a very non-polar, greasy molecule. Soluble in fats, not soluble in water, hard to get rid of because you'd have to, basically either get it out of the fat or lose the fat itself. And losing the fat itself is difficult, trust me. So, That's not medical advice. We're not saying eat as much, oh, great, I can do with vitamin C what he does with Diet Mountain Dew and have infinite quantities. No, it's not like that. I'm not saying eat as much vitamin C as you can possibly purchase, but extra vitamin C is generally able to be excreted because it's water soluble. So there are conditions. If you have too much vitamin A, you can look up on the medical stuff from NIH or something about hypervitaminosis A, which is a condition that you get from too much vitamin A. And it gets stored in your body and causes problems. So water soluble versus fat soluble, thanks to structure, molecular structure, and like dissolves like. There are other factors. Pressure. Pressure has effects on solubility. This is mainly involved in liquids dissolved in gases. Gases dissolved in liquids. Well, they're dissolved in each other. Anything goes, right? Gases dissolved in liquids would be the way to say it, probably. The equation that's given there, S gas, that's the solubility of the gas, equals Kh times the pressure of the gas. That Kh is a Henry's law constant. This is Henry's law. I can't remember if Henry was the first or last name of the person. It probably could have been either. But Henry's law is that mathematical relationship where Kh, the Henry's law constant, is a particular thing for a solute-solvent combination. So, like there's a Henry's law constant for CO2 in water, and there's a Henry's law constant for oxygen in water, and so forth. So there are lots of Henry's law constants. They're data. They've been determined by experiment. You can look them up. Or I suppose one can make a task in a lab out of determining the Henry's law constant somehow. But they're data. But the solubility of a gas depends on the partial pressure of the gas above it. And you see this, for example, if you're addicted to something like this, like I am. Okay, why the whoosh? Thank God I can drink it finally. I'm waiting forever. Why the whoosh? What's the whoosh from? Extra CO2 pressure. Okay, they pressurize it. There's a little extra CO2 there. We know if we leave it open, it's going to go flat. Eventually, the CO2 is going to, bubble out until the partial pressure equalizes. But they pressurize it with a little extra CO2 to keep more CO2 dissolved. That's why it fizzes, because of the CO2. All hail CO2. Wonderful. So higher pressure, higher solubility. So if you want to keep a gas soluble in water, you increase the pressure of that gas above your solution, like bottling a beverage. Okay, so opening the cap or popping the tab, and you hear that whoosh. That's because pressure is decreasing, and some of the gas is now coming out of solution. And you see the bubbles in the beverage. This is what goes on if you hear someone talking about a condition called the bends. The bends is a condition that is gives me the heebie-jeebies just thinking about it. If someone's working underwater, where the pressure is very high because there's a lot of stuff above you causing the pressure. I mean, if you're at high altitude, there's less air above you in the atmosphere, so the pressure's lower. But imagine if you were underwater, you have all that atmospheric pressure, plus now the weight of the water. High pressure above you, gases would be more soluble in your blood. If you came up too quickly, let's say you were scuba diving, deep sea diving, and you came straight up, it wouldn't be a good idea, because the pressure is going to decrease, and the pressure increases very quickly as you go underwater at pretty high depths because of all the mass of the water above you. The gases become less soluble, and they will start literally bubbling out of your blood in the veins and arteries and capillaries, and it just sounds painful to think about. I get the heebie-jeebies just thinking about gases bubbling out of your blood. But there are all kinds of dissolved gases in your blood. There's the O2 and CO2 and other gases that are in the air, right? You can't help but inhale all those other gases when you take a lung full of air, and some of that can get taken up into the blood. It hopefully largely gets exhaled, except for the oxygen or CO2, whichever is coming or going. But the bends are at worst, at best painful, at worst they can be deadly. So they advise if you're diving, without a vessel, if you're just, with scuba tanks and stuff, at some appreciable depth, to come up almost like you're taking switchbacks up a mountain. Go more horizontal than vertical. And that way, it's like, remember when we were talking about thermodynamics, a reversible process? If you do it as a reversible process, little increments, instead of an irreversible process, which would be straight up. that would be a bad way to do it. So the bends involves this Henry's law. The gases are much more soluble at the higher pressure at depth underwater. Temperature also has an effect on solubility. The temperature effect is one of these conundrums that we get. Generally, if you increase the temperature of a solute, you can increase the rate that it dissolves at, because you'll increase the kinetic energy and it'll dissolve more quickly, but it depends on what the solute is as far as how much will dissolve. This is the killer. Now, gases. The other thing about the drink here, let's say you have a drink. Let's say you've already opened it, but let's say you have a bottle that you can put the cap back on. What's the other thing besides putting the cap back on that you always do if you want to keep your soda from getting flat? Fridge, right? You keep it cold. You throw it on ice or you put it in the fridge, you keep it cold, because gases are more soluble in liquids at lower temperature. So CO2 is more soluble in water at a colder temperature and less soluble at a higher temperature. So if you let this get warm, it's going to get flat. And flat soda stinks, right? I mean, if this lost all the dissolved CO2, it would be like, useless warm yellow water, right? Thank God there's caffeine in there for some sort of redemption. But, gases are less soluble at higher temperature, more soluble at lower temperature. Think kinetic molecular theory. Higher temperature, faster moving molecules, they can escape the solution more quickly. For solids, the effect of temperature depends on the heat of solution. There's a figure that it looked like we skipped earlier, but we didn't totally skip it. We were just passing by it for a moment and then getting back to it. One more bump. It might show up, it might not. Here we go. Figure 13.19. It's back. Now it's gone. You never know. Now it's back. Now you see it, now you don't. It's like an eye exam, right? Is it better here? Is it better there? Is it more red? Is it more green? Can you see the figure? Can you not see the figure? Here's a figure that shows the solubility as a function of temperature for a bunch of different compounds. Notice that most of these lines have a positive slope. Some are more straight lines, some are more curved, but they all have a positive slope except for one. The ones that have a positive slope, think about it. If it's more soluble at a hotter temperature, the ones with a positive slope, like potassium nitrate, the green line, increases really fast, gets more soluble at a hotter temperature. What does that mean about the enthalpy of solution? If you're adding heat and it makes the process occur to a greater extent, it shifts to the right in equilibrium terms, that would mean it must be endothermic, right? It must be endothermic, a positive delta H, because a positive delta H heats like a reactant. If you add a reactant, you shift toward products. You dissolve more. So all of the substances there that have a positive sloping curve have an endothermic heat of solution. The one that we already saw was NaCl. Right? It was endothermic, but not by much. Right? It was like 4 kilojoules. That was it. And notice the line is almost flat. It's barely positively sloping, which goes with the fact that it's got a barely positive heat of solution. Well, that's fine. The cerium sulfate on there is a negative sloping curve, which means that it has an exothermic heat of solution. Not drawn on here for whatever reason is NaOH. NaOH we know is exothermic for heat of solution. That would also be a negatively sloping curve. We'd need data points to know how to plot it. I'm not going to just draw a curve on there willy-nilly, dilly-dilly, whatever, because I need data. Okay. So remarkably, that's where we got earlier, even without the computer screwing around. Okay. So that's where we're at. We'll do better the next time. Well, thanks for hanging in there. And if you have the form for STEM and you didn't give it